just say, it's an array of, not just integers, we'll just say an array of numbers. So you could have, fractions, or floats. And it's, positive or negative, or 0. So you just have some array of numbers. Think of these as maybe floats. Okay, and the question is, the problem is, find the subarray. The subarray would be, some portion over here going from I to j, with the maximum product of entries. Okay, so for example, if we're looking at this subarray from I to j, the product would essentially be the product over all k going from I to j of ak, right? Just the product of all entries. And so the question is quite simple. It's just, find the subarray with the maximum product of entries. Okay? And so you'll see that because there are potentially zeros, there are negatives, it gets a bit complicated. If they were all just positive integers, it's obvious you just take all of them. But because you also have floats, so maybe by multiplying by something it actually becomes smaller, so on and so forth. And if you multiply two large negatives, then it becomes positive, right? So I guess that's why it's a LeetCode problem. Question make sense? Okay. So the thing is, when you see such a problem, actually, let me ask you, what is the first thing you should do, algorithmically? And this is what I did. The first thing that you do when someone brings you a problem of this form. Yeah?
You think of a naive, inefficient solution?
Exactly. You start with a naive brute force solution, and it's highly unlikely. So for almost all the problems of this kind you'll see, there's usually a solution that uses a bunch of nested for loops, right? Whose analysis is very easy to do. Does that make sense? Right? And this is what you should do anytime you see such a problem, or any problem. Whether it's in an interview or it's actually when you're trying to solve something. Right? You start with the naive, simplest solution. Then you use all the techniques that we learned, like either data structures or dynamic programming or divide and conquer, to see if you can improve on those solutions. Right? But this is the method. Okay, so what is the naive solution? The simplest solution you can come up with. Yeah?
Find the product for every possible subarray.
Find the product for every possible subarray and just maximize over that. Right? Pretty simple, right? So if you ever get this in an interview, that's the first thing you should say, mostly to buy yourself time to think about what to do next. But also to convince the person that you're talking to that you understand the problem. Okay? So this should always be the first step, which is find a naive brute force solution. And I always tell, students or even people that I'm mentoring on algorithms, sometimes in practice, the naive brute force solution is good enough. Right? There's a quote that says, premature optimization is the root of all evil. Right? So sometimes you shouldn't try to overcomplicate. Maybe in an algorithms test, the question is different, but if you're actually trying to deploy this, and if your problem is small enough, maybe the naive brute force solution is good enough. Okay, so the naive brute force solution, as was correctly said, is just, compute. So I'm going to just call this quantity product ij, which is just k is equal to I, j, ak. For all I less than j. Okay, so we'll just compute this product for everything. Okay, so how long does it take to compute one of these products? Yeah, O of n, right? You could just basically loop over all the k's, right? And so if you put it all together, you get a triple nested for loop. Okay, so I'll just write this down. So, I'm going to write code and, either I'm going to write pseudocode or I'm going to write something, but I might make indexing errors and that's not that important, right? So I might be off by ones just to make it look easier. So, you can say, for I going maybe from 0 to n minus 1, for j going maybe from I to n minus 1, we can basically compute what product is. So then, okay, so maybe I'll just write this out. So initially, I can initialize product ij is equal to 1. This is just like an initialization. This is just initialization, initialize. And then I can say for k going from I to j, product of ij is equal to product of ij, times a of k. Yeah, I think it's probably correct code, right? So maybe at an interview, they'll just make you do this, and that gives you about 5 or 10 minutes to buy time to think about what to do next. And so what is the running time? It's pretty easy. It's n cubed, right? Basically, you have 3 nested for loops, and so you get O of n cubed, or whatever, theta of n cubed solution. Right? So it's an O of n cube algorithm, or to be precise, I'll say it's a theta of n cube. It's exactly n cubed because it's a triple nested for loop. Okay? So then you say, okay, how do I improve on this? And your hope is maybe you go from n cubed to n squared or n squared log n. Like somehow you shave off one of them by either using a data structure or using one of our tricks or using one of our methods. Yeah? So far, so good. And so you look at this and you think, okay, so whenever you have a problem with this form, you should always think, maybe I should do dynamic programming in some form. Right? It's a natural, given that we've seen all these examples of dynamic programming, you say, can you do some dynamic program? Can you save maybe another factor? Now, I've written this in a particular way that sort of suggests maybe you can. Right? So your aim is to basically compute all of these products. And what you did over here was just you did a separate for loop for each of them. Seems a bit wasteful. So can you shave off something from this? Can you improve this a bit? Yeah?
If you keep if you cache all the computations in some table,
Yeah?
product of I, j minus 1 times product of, or the array of j will give you the full answer, so you don't need to do the third loop.
Okay, good. Right? So you observe that product of ij is basically equal to the product of ij minus 1 times aj. Right? I'll write down this thing. So, by the way, so hopefully this is clear, right? Naive n-cube solution, this is your starting point. Then you think dynamic programming. And again, so dynamic programming can, often the way I've taught it is you think of a recursive algorithm and a recurrence, but fundamentally what it is right, at some point, it's also related to, I have some table of entries that I want to compute, and instead of doing a separate computation for each, I could basically look up some other entries and do it. Okay? And so, this isn't maybe formally dynamic programming as in building a recurrence, but it's basically the same idea. What you try to do is you say, well, if I look at the product of ij, this is equal to the product of I j minus 1 times A of j. Does that make sense? Right? So essentially that third for loop over k is like recomputing essentially the same thing in each go, but one more. Right? So you could have just stored the answers and used this. Does this make sense? So you'd essentially you'd save one for loop, and you'd end up with an n square solution. So I'll write it out a little bit more. But is this clear, the idea? So I'm going to draw this out basically as a picture, and I might not write out the pseudocode, but hopefully this picture should make it clear. So when you have these entries, so I'm thinking of I going from 0 to n minus 1, and I'm thinking of j going from 0 to n minus 1. Right? And essentially, because j is always greater than I, like these are the only entries that I care about here. And so what I'm saying is, if you fix I, you can basically loop over all j going from I to n minus 1. So if you fix I, so if you look at any one of these rows, right, so what are all of these rows? These are rows where you're looking at product I, j, where j goes from I to n minus 1. Right? Those are all of those entries. You can compute all of these with a single for loop. Right? Just by storing all the entries. Does this make sense? So you can do all of these with a single for loop. Clear? Questions? Yeah.
Shouldn't it be the lower?
Have I drawn this the wrong way?
Because it goes from I to n minus 1 and
Damn it. Yeah, you're right. Okay.
I guess if you flip the x, yeah.
Thank you. Yeah, you're right. Yeah. Thanks. Yeah? So basically, you've got all of these entries here, and technically you're filling them up in that order. Right? So you can fill all of these up in this order. Make sense? So single for loop, so all of these entries, all of them, where you fix I, can be computed in O of n, and the total running time is O of n squared. So the odds are you probably got the job at this point, but still, you could try to do more and then negotiate for a higher salary, right? So again, this isn't dynamic programming in the sense that we wrote a recursive algorithm, but there's definitely some recurrence, and there's this notion of a table, and you think of a table and how to fill up the table, right? So that paradigm is useful. Okay? So in your typical problem, once you're down to n squared, the next thing you could potentially hope to get is n log n. Yes, there are these crazy complexities like n to the log base 2, 3 or something, but that's rarely something that you're going to actually encounter unless you're doing research in algorithms. Right? So the typical thing you're going to hope for at this point is, how do I get from n squared to n log n? Right? And so there are usually two methods to do this. The way that you go from an n squared to an n log n is either you use some data structure to store things and then you do lookups with log n, like a heap or a red-black tree, like a self-balancing tree, or you do divide and conquer. And you try to get something that looks like merge sort. Okay? Like merge sort, again, is like this typical example where you have a simple n-square algorithm, which is like insertion sort, and then you do divide and conquer, and you get it down to n log n. And so what I'm going to do is that show you that, okay, you can actually do divide and conquer here. And if you just try to think about how you'll do divide and conquer, you'll end up writing the algorithm for it, and you'll get n log n. Okay? So let's do that. So let's go back to... So any questions at this point? Hopefully this is, pretty clear. And again, maybe if you actually had to do this in practice, if your n is like less than 1,000, then this is enough. You're done. Now you could code this up and you'd have solved your problem. But maybe, n is like 1,000,000, in which case now you have to do something more. Okay. So how would we do divide and conquer here? So remember, what we want to do is we want to find... So again, in the interest of, teaching this in a lecture, I'm not going to distinguish specifically between finding the subarray or actually finding the product. But you can see that by changing the indexing, just the way we do in dynamic programming, like you keep track of indices rather than keeping track of the actual number, and you can actually get the subarray instead of the product. But the way I'm going to do this is I'm just going to find the product. Okay? And once we have the solution, we can discuss how to get the actual subarray. Like, how do you get the indices I and j? Okay. So suppose you want to do divide and conquer. You'll say, well, I'm going to split this into two parts. And I'm going to do a separate recursive call for L and R. And just by recursion, I'm going to assume that I get the solution for L and I get the solution for R. Okay? So what does this mean? So what this is going to do is we can get the max, I'll call it the subarray product in L. And from here we get the max subarray product in R. Okay, and so that I don't have to write this over and over again, I'm just going to call it the max subarray product, the SAP. Okay? So I got it in L and I got it in R. So this is probably going to be something here and something here. Okay, so now what? How do I actually combine to get a solution for the whole thing? What are the subarrays that have not been considered by these recursive calls? Yeah?
The ones that start in I and end in R.
Start in L and end in R. Yeah, exactly. Right? So the problem is there are subarrays of this form. These have not been considered by the recursive calls. Yeah? So how are we going? So what we need to do is now maximize the product over these. Okay? And if we could maximize the product over these, essentially in linear time, in O of n, then we would get something that's going to look like merge sort in terms of its running time, because it makes two recursive calls and then it makes this linear time thing. Yeah?
Can you find one in the middle by just multiplying both max subarrays from L and R?
Multiplying this and this?
Yeah, whatever they both find, you multiply them and then get the max subarray product.
The problem with these is that these don't straddle the middle necessarily. So for example, this could be somewhere here and that could be somewhere there. So you want things that are straddling the middle, and that's not necessarily these. But you're almost there. I mean, like, actually, if you think about that, think about what you just said a little bit more, you have a procedure to find it. Right, does this make sense? So, okay, so now, this is the nice thing about divide and conquer, is that you start converting your more general problem into a more specific version of the problem. And if you solve that more specific version, you actually get a solution for the whole thing. So let's look at this problem instead, which is really, this is the combine problem. The combine or the conquer step, which is, okay, that's your midpoint there. So you want to maximize SAP over subarrays crossing the middle. Does that make sense? So again, once we, so he's here. He's the one who asked me this question. So I'm solving your LeetCode problem here now. Okay, right? So you want to maximize the subarrays of this form. Yeah?
But potentially the subarray of L or R could also be, or the max subarray of L or R could be
Bigger. But that's fine. Then you just compare the three, right? Yeah. Right. So once you maximize these, then you have these three options, and you just maximize over those, and you just output that. Yeah. Okay. So how do you do this? Does this make sense? So I give you an array, I give you a midpoint, and I say, find me the maximum SAP over the subarrays that cross the middle. Without, of course, doing the n-square solution. I mean, you could do it in n-square just by, we already know how to do it in n-square. The whole point is to do better than n-square here, and then hope that if you plug it into a divide and conquer recursive mechanism, you'll get an improvement. Yeah?
Don't we already have a function that does this? Can't we just call this function that solved L and R for this middle chunk?
No, so what L and R, the recursive procedure, you give it an array, and it'll just return the max SAP in that. It could be anywhere, though. It's not necessarily going to cross the middle. So so the thing is, we haven't really written our procedure yet, right? So there's a bit of circularity here. But what am I assuming? I want to do divide and conquer, so I'm going to say, suppose there is a procedure, like by recursion, I could solve this problem. Now, what am I solving? I am only getting the maximum subarray so I give it some array, and it spits out what the maximum is in here. That maximum, maybe it's over there, maybe it's over there. It might not necessarily cross the middle. So specifically, in this example, wait, hang on. So let me first. So by and large, firstly, by the rules of recursion, you're not allowed to call your recursive procedure on something of the same size.
But we can just take everything past what the subarray of L returned and everything before what the subarray of R returned.
But how do you know that maybe the max is actually going to use all of it and then something here? Or maybe it's going to use part of it. We don't know. Maybe it could. Yeah?
Maybe we could start at the middle.
Okay.
Move to the left and find the largest product there.
Okay.
And then we could start at the middle, move to the right, find the largest product, and multiply.
Okay. Does that make sense? There's only one case that you've missed, which is the numbers can be negative. Yeah?
I was thinking, you said that an even amount of negatives, basically.
Right.
Yeah.
But how would you, so it's even simpler than that. But yes.
Can we just reuse the recurrence from the DP table thing that was in ON?
Which is? To do what?
To sort of basically, it's just one for loop, but it sort of uses the trick where we know that product ij is equal to product ij minus 1 times j.
Right.
So could we do that to loop through all i's?
You could, yes. So essentially, so think of it as, so your I is here and j is here, which is similar to what he was saying, was that you could loop in this direction over I, find the maximum subarray that ends at the middle, then find the maximum subarray that starts in the middle, and then just take the product of those two. And I'm just saying there's one corner case, which is that, I mean, the way to maximize your subarray is if both things are positive, that also is positive, but if both things are negative, that also is positive. So if you want to find the maximum, there's just one additional step. It's almost the same, yeah?
Maybe you just track both the largest negative, largest positive.
You just track both, or I guess the smallest negative and the largest positive, but yeah, by absolute value, right? Exactly. So I'll write this down, but I'm just saying, run a for loop in this direction that just keeps track of the largest positive product. Then run a for loop in this direction that also keeps track of the largest positive product. Okay? Yes?
Sorry, I'm just confused. How is the first LR diagram different than that last one?
How is that different from this? You're making a recursive call in here, but here you're not making a recursive call. You're actually computing the maximum SAP over subarrays that are crossing the middle. The whole punchline is going to be that the ones that cross the middle are easy to do. Okay, so I'll say this, then I'll write it. So you compute the max positive in this, of this kind, and the max positive of this kind. And so the max, if you look at the max that crosses the middle, like, okay, so let's do this. So let's just say that max was ij, right? So the product of ij is equal to the product of I to n over 2 times the product of n over 2 plus 1 to j. Why? Because I is less than n over 2 and j is greater than n over 2. Right? Because it's crossing the middle. And if it's exactly n over 2, it's one element, then it's easy. Okay, so there you go. Okay? Yeah?
To confirm, the negative case where you track the smallest negative and the highest positive, it doesn't apply to the SAP of the left and the right, only the...
So the thing is, these are recursively doing something. And actually, in that recursion, you'll see that this work is going to be done there. Right? Because I haven't really written out the procedure yet. When I write out the procedure, you'll see that the recursive calls also have to do exactly the same thing. But, so, does this make sense, right, this formula? So how do you maximize this? You could maximize both of these being positive, or you could maximize, or technically minimize this being negative and this being negative, and that will be positive. Right? Does that make sense? So essentially, yes?
Are the entries guaranteed to be like integers?
No, they could be floats.
Like, what if you have like 1/4 and 1/4, like the maximum on both sides? Don't you get a smaller?
Well, I mean, you still have to look at what is the maximum that you're going to get, straddling each. I'm just saying that find the subarray. So if you actually have to take the middle, and so then you would probably not, you would look at, suppose let's say all of them were floats less than 1. Then what this would do is, the way that you get the maximum product here is just to take one entry. Right? Does that make sense? Because you wouldn't take more, because then that would make it smaller. And if the subarray was actually completely contained in the left half or the right half, well, then your recursive procedure would have figured that out. Your only problem is that you're worried that the maximum might actually be crossing the middle. Because if it wasn't crossing the middle, the recursion would find it out. Now, how is the recursion going to find it out? Well, that's the thing about divider. You don't have to specify that. When you write out the entire procedure, it will automatically figure it out. Right? Until you get used to it, it always feels like magic. And then at some point you get used to it, and then it's obvious. This problem is like you're never in the middle. It's either obvious or it's magic. But does this make sense? Right? So you have to write one for loop to find the maximum positive one for loop to find the minimum negative, and then the same thing over here. So in linear time, that is basically constant number of for loops, you can find this out. Right? Does that make sense? I'll write this, but Does the overall logic make sense? So at this point, you're guaranteed to get the job. Like, at this point, you can start negotiating for a higher salary, right? Yeah.
So maybe I'm behind. The prod I and Q, those are indices of the subarray, right? So it's every element in between those two.
Yeah, this product means you're getting everything in between.
Okay. And it's not a sorted array.
It's not sorted. It's not sorted. Actually, you shouldn't sort because you're being asked about the product with respect to these indices. So if you sort things, you'll basically screw that up, right?
Because otherwise, if it was sorted, you could just take like the biggest half of the.
If it was sorted, then you could just start at one end and you would just, you could go down. Basically, you just pick up everything that is, that's more than one, and then you'd be done. And then you have to do something separate for negatives. It's a bit more complicated, but we're going to see that you can solve this just for any array. Yes?
This algorithm looks like some kind of greedy algorithm. So why do we have to divide and conquer concept for something?
Because you have to, this is not enough. You have to make the recursive call for the left and the right.
So choosing the middle index, just traversing 0 to n. I think we can find the results exactly the same with the divide and conquer.
No, say that again.
I mean, actually, the reason why we are using divide and conquer for choosing the middle index.
Not for choosing the middle index. It's like this. It's like saying that, look, let me look at this array. Just take the middle. Now, there are three possibilities. Either the maximum subarray is entirely in here, or it's in here, or it's crossing the middle. We don't know which one it is, right? So this procedure here only takes care of this case, and recursion will take care of the other cases. That's why it's divide and conquer. Does that answer your question? Yeah. So you might think that this part here is kind of like greedy, which is, I guess that's one way of looking at it. But I wouldn't necessarily think of it as greedy because it's just there's no real choice that you're doing. It's not like you have multiple choices and you're saying, I'm going to do this one as opposed to that one. You've just observed that, that to maximize the subarray ij crossing the middle, it's enough to maximize the subarray where one of the indices is fixed. And when one of the indices is fixed, the problem is easy. Okay? And then, of course, you have to do this for the negative one as well. So this I'm going to write out in English. I'm not going to write out in code because I'll probably make a mistake in some indexing or something. But let's just go ahead and do this. Okay. So we're going to have our max sap. So let me, as a procedure, give it two indices. Okay, so this is a bit overloaded. So I want to write out the general procedure so that there's no confusion. I'm just going to imagine that at some point in your recursion, you're really solving the problem on some subarray, right? Because you're making these recursive calls. So suppose we're basically solving it. We're solving the max sap in this portion. Right? So this is the portion that I care about. There's low, there's high. And now let me sort of describe this procedure. So let me just number the steps so that it's clear. So the first thing I do is I compute, or I guess technically I should say recursively call max sap low to mid, and I'll tell you what mid is in just a minute, and then call max sap mid plus 1 to high. I should have said mid is equal to the low plus high divided by 2. Sorry, this is a bit messy. Okay? Right? So middle is just, I compute whatever that middle index is, then I make a recursive call to the left, I make a recursive call to the right. Okay, now, right, so these are the two recursive calls that I've made. Then the next thing that I do is I say using a single for loop, compute max of product I to mid, where I is in low to mid. Okay? Then using, again, a single for loop, compute max the product from mid plus 1 to high, mid plus 1 to j, where j is at least mid plus 1 going up to high. Okay? So I'm just, to give myself names, I'm going to call this thing A, I'm going to call this thing B. Then I do the same thing, I'm just going to write it out as step 5 using single for loop, compute the min, right? So you have to do the smallest negative one, which is just the min over everything, right? So you compute the min product I mid as before. Let me call this as C, and then also using single for loop, compute D, which is the min of product mid plus 1 j. And then finally, I return the max. So I do A times B, C times D, and then whatever I got from these recursive calls. Okay? So for lack of a better thing, I'm just going to call this thing as L, refer to this thing as R, and say compute max of these. Okay, so modulo some messiness, this is the entire procedure. Does this make sense? Yeah? You see why this works? So, I mean, nice or good or bad, the thing is that, like, someone had said, like, maybe you could try to use some observation about the fact that the recursive solution here should overlap with this or something like that, and actually something like that might even be true. So, but this basically gives you like a complete bona fide result. You don't have to worry about anything about the structure. The only thing that you used was that when you want to maximize over the middle, it's equivalent to maximizing over, this I to n over 2 or n over 2 plus 1 to j, or minimizing both of them, because they could both be negative. Right? So just to be clear, this is the case. You're really considering the case that C and D are negative. And if they aren't negative, it doesn't matter, because when you maximize over here, you'll just take care of it. Okay? Does it make sense? Yes?
Could you possibly just sort the array so that in n log n time, if you're just returning the product and not indices, you could sort the array n log n time and then do a single
No, so as we discussed, right, I mean, when you sort, you destroy the subarray structure. You're looking for the it's not a subsequence, it's a subarray, right? So you can't sort. Yeah. Yeah? Is this written at the stage where if you, had to write code in a leet code example, you could? There are a couple of indices that you might get, you have to be a little careful with, but other than that, it's just a bunch of for loops to compute some quantities and then make these recursive calls, right? So yes, there is being careful with the indices, which is important. But now, since we're thinking more about the logic and the concept of divide and conquer, right? So this is the process. I just want to step back and say, like, how would you approach it using divide and conquer? It's not obvious that divide and conquer would work. But you would say, okay, let me break it into two parts. I get the recursive solutions in each part. What are the solutions that are not being considered? And then it's the ones that cross the middle, right? And then you kind of have to stare at this and say, okay, this I can actually get in linear time, in O of n, and then I have this, right? Yes?
I feel like we've solved similar problems like this before where we're trying to find some maximum subarray. So what exactly makes us, like, is it the fact that there could be negatives and that there's like floats that makes divide and conquer more appropriate for this one specifically, or?
I mean, the thing is, if everything was positive and everything was an integer, then the maximum is just the product of everything. Right? Then the problem is just not that interesting. It's when there are floats that actually it becomes interesting. Yeah?
So we covered a dynamic programming approach, but for divide and conquer, we're not memoizing anymore.
No.
That was just to show us how the subproblems are formed.
I mean, it's more like that was an approach that got you to n squared. I just wanted to say that, like, I mean, normally when someone teaches, they'll just show you the optimal thing and say, this is what the answer is. But I don't want to do that. I want to say, look, this is how you would, if you actually had to think about it, you would start, it's natural to try to do dynamic programming in a problem of this form. Right? Anything that looks like it's a table, it's got arrays, you know, you should always think, can I do dynamic programming, and see how far you get. And this is about as far you'd get with that. You'd say, okay, but it is useful because it gives you some, it allows you to improve on that brute force. Right? Yeah.
So what should we be looking for like in a situation where divide and conquer would be better than you said the dynamic, if you look at NC tabling, then dynamic might be the best way.
So unfortunately, it depends on the problem, and it's not obvious. So you have to try both, and you have to see how far you get. Usually, with dynamic programming, the complexities you get are always like, you know, n cube, n square, n. Like, it's just the size of the table. Maybe you, like in that problem, the additives, the homework problem is like n root n or something. But again, it's usually just the size of the table and then how many entries you need to look up. So the complexities you'll get are quite obvious, right? And if you're really trying to break, you know, go below n squared, for many problems, it turns out that divide and conquer was usually the path. Okay? Okay, so what is the recurrent? So now, once you write down this, you know, this mess, you have to give a runtime analysis, right? And so, what is the runtime analysis of this? I think I've already said it multiple times. Yeah.
O of n log n.
Huh?
Is it O of n log n?
And why?
Well, I guess every time you divide it into, it's sort of the opposite. If you have twice as many, you have half as many things to go through. And the combining bit is O of n. So each step you're doing it on something that's sort of half of the size of the previous thing.
Yes. Okay. I mean, I was going to say, like, you could just write down the recurrence, the running time recurrence for this. Right? Whenever you have a divide and conquer, you have to write down the runtime recurrence. And the logic will exactly be, you know, what you said. So, is this clear? Any questions about this procedure? Does this make sense? Yeah? Okay. All right, so let T of n be the worst case running time of the above algorithm. Okay, so now I'll just maybe ask you, what do you get? Do you get T of n is less than T of n over 2 plus O of n? Do you get T of n is less than 2T of n over 2 plus O of n? Or do you get T of n is less than 2T n over 2 plus O of n squared. What do you get? Tell me. Now, if this procedure is clear, then hopefully you should be able to figure out which of these options is the right one. Now I'll give you a couple minutes. Yeah, okay, so what's the answer? It's this, and you see why, because there are two recursive calls made compute recursively like that, and they're basically of size half, right? So if the whole thing had size n, then this had size n over 2. So two calls of size half, and then all of these are just O of n steps because they're single for loops. Great, right? So once you see this, you should just say this is O of n log n. Right? You don't actually have to even like write out the tree or anything, at least for the sake of this course. If you say this is the running time I get and I get O of n log n, so, okay, good. Yeah? All right, so where did we start? We started from n cubed. We made some simple dynamic programming observations, got to n squared. Did divide and conquer, it's more hard work, and got to n log n. And this is not the end of the story, as it turns out. So, but this is, it's 50 minutes, so let's take a break for a couple of minutes. When we come back, I'll show you how to improve even on this solution, again using divide and conquer. All right. So, by the way, maybe I should also tell you, like, there happens to be an even shorter solution that's more efficient. But the problem is, and as has been said, like, it's not obvious how you would get there. Whereas this, to me, is a more sort of structured way of thinking. And eventually, you could get to this, like, really short optimal solution. But usually, you have to follow all of this. And the reason why I wanted to do this was it's like a typical LeetCode question you might see. And this gives some way of approaching and how you can use divide and conquer. So anyway, so the thing is, if you wanted to go below this, how would you do that? This is even more tricky. But let me show you how you could do it using divide and conquer. And again, using the same logic. So let's go back to this picture. So what we had is, like, we broke it into 2 steps. You made the recursive calls, and then you had to solve this. And this took O of n time. Excuse me. And so that was, just to draw this picture again. So you did this recursive procedure on the left. And so what this returned was some product of this form. And then what we did in the procedure, excuse me, which is all of this. And of course, steps 3 and 4 are kind of like, steps 5 and 6 are a mirror of 3 and 4. Right? It's just this positive and negative thing. So let's just think about the positives for a second, just to keep it simple. And we'll worry about the negatives later. Assuming everything is positive. What you did over here was you kind of found the max of this kind, the max over here, took the product, and then maximized over these 3 things. So this was A, B, and sort of using notation, I call this L and R. So you maximized A, B, L, and R. Right? And computing this was your linear time step. Now suppose the recursive procedure also told you what this max was. So I'm going to ask more of the recursive procedure. I'm going to ask the recursive procedure to return L and also return A. I'm going to make this recursive procedure return R and P. So my problem is now kind of, it's almost like I'm changing the problem. I'm saying the problem is to return not just the maximum subarray, but also the maximum subarray. So return 3 things. The maximum subarray that's overall, the maximum subarray that involves one end, and the maximum subarray that involves the other end. So return all these 3 things. So I'm actually asking the procedure to return more things, but in the end, it's going to be easier to get an algorithm with that. Does this make sense? So I say that this procedure has to return 3 things. So now I'm going to say the procedure needs to return 3 values. First, it has to return the max subarray just as before. Then it's going to have to return something that I'll call the max L subarray, which is the maximum that starts at one end. And then it also has to return the max. It has to return all these 3 numbers. Does that make sense? So this is my problem. I just said my problem is return all these 3. Now you could say, obviously you can do it in n log n, because returning the first one we showed how to do in n log n, and returning this is easy. This is just O of n for each of these. So overall you could do this in n log n. But now I say that if you want to solve this problem with divide and conquer, it actually becomes easier. And this solves the overall problem more efficiently. This is a bit tricky. Yeah. Question?
It was half raised.
Half raised, okay. So you have half a question. So this is how I approached it. I said, look, I really want to find A and B to be able to do that combined step. Now, what would be nice is if the recursive procedure actually told me what A is, and this recursive procedure told me what B is. But if that's the case, then this procedure, which itself was called recursively, has to send the appropriate quantity as well. So it has to be able to compute the max L and max R using the max L and max R from here. Okay? Yes? No? So now I'm going to draw this out in pictures, and then then you'll see how this works. So I did divide and conquer. Now, from the recursive step, I'm going to get 3 numbers. Right? I'm going to get the max over here that I called L. I'm going to get some max of this form that I called A. And I'm going to get some max over here, and I'm just going to call this A prime. And what I get from here is I get R. This is B. This is B prime. Right? This is what I'm doing divide and conquer. So I got these recursively. Now I have to be able to output the same 3 equivalent quantities for this one. Okay? Let's not worry about the negatives for now. Okay? Okay. So now for this, the overall array, right? This is the overall input. Is this picture making sense? Right? So these are all from recursive calls. Right? This is the left recursion, this is the right recursion. Now for this, if I want to compute the max subarray over the whole thing, yes?
Why do you need A prime and B prime?
It's a good question. You'll see that in a moment. Because you don't need A prime and B prime the way this is set up, but you'll see that this procedure also has to return its subarrays of this kind, and it's going to need A prime and B prime to do that. Because you don't know if this subarray has to return the A or the B. Like, it has to return something. Good question. Well, once all of this fits, you'll see that. Okay. So this is the overall. So I'll call this the full input, right? This is the full input. So I'm looking at the full input here. So for the full input, what is the expression for this? How do I compute this? So I got these 3 values, and I got these 3 values. What should I output here? It's the max of something. What? Yeah? And? L and R. Right? A times B, L, and R. Again, we're looking at the full input here, right? So if I want to get this, and I want to get the max of this kind, because this procedure has to return all these 3. What do I need? Yeah?
Max is A prime and potentially A prime B if A prime is the entire.
Good, right? So it's a max of A prime and the max of multiplying everything here times B. So how do I know how to get that? How do I get the max of all of this? I could actually just ask the recursive procedure to send it, and then just send it further on. So it's going to return not 3 things now, but 5 things. So return A prime, A, L, and it's also just going to return just the product of everything. And this is also just going to return, so it has to return 4 things. So it has to return the max of this kind, the max of that kind, the max overall, and just the product of everything. And once this gets a product of everything, it can just take the product and send that forward. So this is the whole product. So I'll call this is, okay, so I'm really running out of symbols here, but I'm just going to call this X and Y, sorry. So it's the max of A and X times B. So how do I get that? This is going to be the max of B prime and A times Y. And what is the product of the whole thing? Well, this is just X times Y. Okay? This is constant time now. So I get the 4 values from here, the 4 values from there, and I can just multiply it, and I can send the 4 values for this one as well. No for loops anymore. Actually, this procedure, when you write it down, is going to be even simpler. To really get it, you should code it. You should, if you write the code for this, it'll become pretty clear. But does this make sense? Right? Okay, so let's see how much time we have. Okay. So to me, I can write the code, but I think the pictures to me are like the main thing. You have to, yes?
X and Y, that's the middle cross.
X and Y is just everything. It's just the product of everything. You need the product of everything because the maximum starting from the left for the full input could either be contained entirely in the left, or it might have everything in the left. And if it has everything in the left, then it's everything in the left times B. So you need that product of everything to help you compute, right? But what's nice is once you get the product of those, you could just take the product of that to send it for the because when you define a recursive algorithm, it's like you're defining a contract. You're saying, like, I want the recursive procedure to give me all of these quantities, but then that procedure also has to be able to send all of it to whoever calls it. Yes?
But this looks like you're still computing all possible products over all possible subarrays in the left and right side, which...
Where? I'm just doing, so this makes 2 recursive calls. The recursive call to the left returns 4 numbers. The recursive call to the right returns 4 numbers. Then this procedure combines to return 4 numbers.
But don't you need to check all possible subarrays in the left? Like, how does that recursive call run in less than n squared time?
Which recursive procedure? Okay, we have to write the recurrence.
Yeah.
Question, yes?
Could X alone be bigger than XB?
Could X alone be bigger than XB? Yes, it is possible. So, because B might be, so X, and then, well, technically, if that was the case, then A would probably cover, well, it's going to be covered by the case that if X was bigger than A prime, then A prime would have actually returned X anyway. Does that make sense? The only way that could happen is that if X was bigger than A, but that's not going to happen. Or if that did happen, then A prime would be equal to X. Is that? So actually you don't, yeah.
But like, what if B was negative?
What if B was negative?
And then like X was then...
So the negatives, you're going to have to return more values. You're going to have to return the negative versions of, there's the C and D, and I didn't draw those pictures yet.
Right.
But I promise you that if you draw those, then you just return, these are all like the max, you also return the mins. And then you can take care of the negatives. But I just didn't want to write like, yeah? No? Look a little confused. You can feel it. Okay? So this procedure is just returning 4 values. And it will combine and return 4 values. Okay, so maybe it is worth writing this out. So I'll call this, this is the confusing SAP method with I and j. Okay, so what does the confusing method do? So first, the 0th step is the mid is equal to I plus j by 2. Then what you do is we'll say that x a prime a l. This is the output of confusing SAP I to mid. The second is you get y b prime r. This is equal to the output of the confusing method with mid plus 1 to j. And then what you do is you just return the max a b l r. Sorry, I have to do this carefully. So first I return xy. This is I return the product of everything. That's the first thing. Then I have to return the max product starting from the left. So I return this one, max a prime xb. Then I return max b prime ay. And then I return max ab lr. That's it. That's the procedure now. I'm assuming all the entries are positive. For negatives, you need to do a little, you just have to do some extra work. I don't want to write it all out because it's already getting confusing. Just assume everything is positive. Assuming it's all positive, but you could have floats. And when it's negative, I promise you, you can work it out. It's just a couple of extra entries in here. It's the same thing. Does this make sense? So I want to return these 4 numbers. And I can return, these 4 numbers are just functions of the 4 numbers that you get from your recursive calls. Okay? Again, there is absolutely no way that you would directly arrive at this solution. Like that just, for most humans, it's not going to work that way. You're going to start by going through that whole procedure, going to the n cube, then the n square, you go down to the n log n, and then you start saying, okay, how do I get better? Yes? No? Okay, so you may have to go and stare at this procedure, but before, suppose you believe this procedure, what is the running time recurrence? And just to be clear, the base case is always like, T of 1 is O of 1. It's just, okay. So is it T of n is less than 2Tn over 2 plus O of 1? Is it T of n is less than 2Tn over 2 plus O of n? Or is it T of n is less than, T of n over 2 plus O of 1? Which one is it? This is your procedure here. Yeah, which one is it? Okay. So you all see it's this. This was just merge sort. This is what we had before. So what we did is we changed the O of n to an O of 1. The combined step has changed. Okay? Now we have to solve this recurrence. This you might not have seen. This isn't as common. Does this make sense? So once you get this recurrence, like what exactly is T of n? So we'll do the tree method and we'll see what the answer is. Questions? Make sense? Sort of, kind of? So again, like, the way to do this is go back, figure out what to do when there are negative entries, and you'll see it's just adding, instead of the maxes, you have to add some mins. You have to add some minimums. And it's exactly the same logic. If you really wanted to figure it out, you would code it. Like, then I think it'll just be crystal clear what's going on. That way you won't make indexing errors. The procedure is pretty short. Actually, this is going back to what you'd asked. Like, this is a pretty short piece of code to write. It's much shorter than the n log n one. Okay? All right. So let's solve. So now we need to solve this recurrence. And this is just some constant. Again, like, there is a master theorem, you can plug it in and solve it, but I always like drawing out the tree because then it becomes pretty clear what's going on. Okay. All right. So how much is the work done over here in each node? Yeah, so O of 1, basically it's like at most some constant C. Right? What is the work done over here? Same, constant C. Okay. Now let's sum over all the levels. So the total work per level over here is at most C. Over here it's at most 2 times C. Over here it's at most, interesting, 4 times C. What's going to be the next one? 8C. So you're going to go down all the way. What is going to be the final step? Yeah?
Is it like 2 to the IC where I...
It's exactly 2 to the IC, right? And so what is I going to be at the end? Log base 2 of n. And so your work at the last level is? Okay, yeah, so 2 to the log base 2 of n times c, right? What is 2 to the log base 2 of n? N, right? So the total work over here is just c times n. So the total running time is equal to the sum over all I going from, I'll say 0 to log base 2 of n of 2 to the I times c, which is equal to c times I going from 0 to log base 2 to the n of 2 to the I. And what we said about any sort of geometric series is that the sum is just dominated by the last term, and the last term is n. So it's basically, if you look at this, it's just n plus n by 2 plus n by 4 plus n by 8, so on and so forth. And this is actually at most 2cn. Okay? So this is O of n. So this simple procedure that is given here is an O of n procedure. And at this point, there is nothing left to do because asymptotically we have completely solved the problem. There's no way you're going to beat O of n, right? Asymptotically. Okay? There also is a solution that doesn't do the recursion and actually does a single for loop and kind of keeps track of things. But again, I don't see how you'd come up with that without going down this route. Okay? So this is sort of like a demonstration of the power of divide and conquer. It's not an easy application, but at least it gives you some way of thinking about it. And what I do recommend is, I think like the n log n1 is something that you should feel like, okay, this I could probably come up with. The O of n1, I agree, is kind of is hard. Okay? Questions? Yeah? No. I'm going to have to come up with the right homeworks for this module to see, to give you the right kind of practice to do these things. I'm not going to expect you to come up with an algorithm of this form. It's a bit much to ask for. in any homework. Yeah? So you know, when you have a recurrence, think of this tree as it's going down, right? So finally, at some point, you're making some recursive call where the size is just like a single element. So how much work is there? You have to say something, because this recurrence by itself there's no such thing as t of half. So at the base case, you have to say what's going to happen in the base case. Just like in any recursive algorithm, in the base case, you have to say, this is what's going to happen. There's no recursion. So it's the same logic. So in all of these recurrences, when it's constant size, when its size is 1 or 2, it's just constant work. This is just to be mathematically formal when you write things down. Okay? So what I will say is that like this recurrence, by now you recognize that this is n log n. You should also probably just memorize this fact that when you have this, then it's O of n. Right? So this is O of n log n. This is O of n. What is this actually? If you were to solve this, what do you get? This is actually the recurrence for a very famous procedure that you're probably all familiar with. The running time recurrence. What is the procedure and what's the solution? What is the procedure for which you get something that looks like this? Binary search, right? Why binary search? Because you make a single recursive call of half the size and you spend a constant amount of time just comparing. Yeah? And so that should tell you what the solution is. It's O of log n. Right? This is O of log n. And why is that? Like, I mean, I can just draw the tree. The tree is just a single path, right? It's just going to be n over 2, so on and so forth. It's at most c, so it's just c log base 2 of n. Does this make sense for this tree? So these are like the 3 famous or common recurrences that you should know and keep in mind. Okay? Any questions? Okay, so I'll make just like a few final comments on divide and conquer. I might not do more lectures on it, because at this point I think it's more of up to you to do more exercises on it, rather than me sort of going on and on and on. And so again, like hopefully the assignment is a good way of just like getting practice in writing up code for it. I would recommend that you write code for this version as well, but I'm not going to grade it, of course. But I think if you wrote the code for this problem, it is a LeetCode problem. Actually, could you send the LeetCode link on Ed so that everyone can see it? And I think that's a good way of getting practice for this, right? So for this, it's not a bad exercise to code up the n log n version. It's not that, like, it looks a little messy, but I promise you it's not going to be more than like 40, 50 lines of code, like maybe even less than that, because these are all just single for loops. You just write a bunch of for loops and do it, right? So if you can code that and then also code up this version, I think it'll be pretty clear what's going on, right? So my general sense is like when you guys code things up, then a lot of stuff just becomes a lot more clear as opposed to the analysis. All right? Okay. So like in the context of divide and conquer, there is another sort of famous result that you should all be aware of, even if you don't sort of know the entire mechanics of how to do it. So I'm just going to write that out. And this is, again, just a fact that having taken an algorithms course with me, you should know, is that if you look at this problem of matrix multiplication. So this is, again, just multiply two n cross n matrices. So here's A, B, and if C is this matrix A times B, so you know that the ijth entry of C is I take the ith row in the jth column. I say k is going from 1 to n. So I multiply a I k, b k, j. Right? This is how you compute the matrix product. So how long does it take to compute each entry? Simple brute force, how long will it take? Yeah? How long does it take to compute one entry of a matrix product? Yeah? Yeah? Well, it's k is going from 1 to n. Yeah, so it's O of n. So actually I'll say it's theta of n. How many entries do you have? N square. So n square entries. And the total running time ends up being basically theta of n cubed. So what this realistically means is if you have a matrix of size 1,000 and you do 1,000 cubed, you can kind of do it. But if you do anything more than that, it's actually pretty expensive, which is why NVIDIA makes so much money, basically, right? Because they have all these operations that helps you optimize these things, and computing matrix products is what's going on in all of these ML models. And it was thought for the longest time that you cannot do anything better than this, until in a fairly shocking work, Strassen in 1971, he gave an O of n is like a weird log base 2 of 7 time algorithm. And so roughly speaking, this is like O of n to the 2.71, roughly. People have implemented Strassen, and there are lots of issues in implementing it, but it can be better. And so the way this is done is this is, again, a sort of divide and conquer. And I won't write out the full procedure. It's not that difficult, but it's very mysterious. Like, I think someone that I knew had asked Strassen how he did it, and he spent many Sundays trying to prove that you actually need n cubed, and then accidentally ended up with this, or he sort of figured this out. So how does it work? Let me give you a simpler question. Just consider 2 by 2 matrices. Right, so you have, this is just 4 entries, A11, A12, A21, A22, times B11, B12, B21, B22, and this is equal to C. So if you write out what C11 is, so this is A11, B11 plus A12, B21, and C12 is A11, B12 plus A22, or A12, B22. C21 is A21, B11 plus A22, B21, and C22 is A21, B12, A22, B. Right? This is just simple. So how many multiplications do you need? 8 multiplications. Right? So 8 multiplications. And then a bunch of additions. So why is this related to recursion and divide and conquer? Instead of this being 2 by 2 matrices, you can break this up into blocks and then just do it recursively. Right? This gives you a recursive procedure also. Right? Where instead of C11 being an entry, it's a submatrix. So you basically apply this logic of submatrices. So think of these as submatrices. If you broke your matrix up into 4 parts. So there are 8 multiplications, and if you do it using divide and conquer, you'll basically just get n cubed again, just like we did for long multiplication. So what Strassen showed Strassen gave a method with 7 multiplications. And just like Karatsuba, like he added these other things. It's pretty crazy like what he did. Like there are a bunch of strange expressions that he came up, but he said you only need to do 7 multiplications and you can essentially get the matrix product. And once you follow all that 7 that you see here is exactly the 7 over there. So if you'd put 8, then you just get n cubed. And so with 7 multiplications and you do the divide and conquer, you get this running time. So the procedure is mysterious enough. I don't want to write out the whole thing. But what I do want to say is that this is something that at least is like a fact that you should know, that Strassen's matrix multiplication, using divide and conquer, you can beat the standard n cube. And this is very similar to beating the integer multiplication. And unlike integer multiplication, where the problem is essentially solved, with matrix multiplication, we still don't know what the fastest algorithm is. People have improved on this and given n to the 2.36 something, but again, those methods are not really feasible in practice. But it's still not known exactly what is the best algorithm to multiply 2 matrices. Sort of very basic problem. Okay? All right, so we're still a few minutes, we have a few minutes left, so I'll just end here. I'll take any questions if you have. But this has been quite a lecture, so I will release all of you at this point. Yeah, go ahead. It's a good question. Yes, there is. But it's not. But there's a different method for sparse matrix multiplication, which is what MATLAB does, or like Python. Basically, when you use TensorFlow or all these things, they're basically calling optimized things in something called LAPACK, which is a package of matrix operations that's usually optimized in C, and that does something faster for sparse matrix multiplication. Yeah. Good question. Yeah. Sorry? No, it doesn't use spectral methods. It actually represented as a graph and solves a graph problem. And if you represent it as a graph problem and you actually basically describe it as a graph, it turns out to be more efficient when it's sparse. Yeah.